Norman Wildberger, and this is probably the most important mathematics video that you're likely to see. It's a video in which I'm going to present rational trigonometry for someone who has not seen any of it for the first time, and I'm going to present it to you in a simple and elegant fashion. If you absorb the lessons of this video, you will be reoriented in your approach to not only geometry, but also mathematics more generally. And you will see that there is a huge revolution in mathematics education which is looming ahead of us. And no amount of orthodoxy or inertia is going to really end up being able to prevent it. So, rational trigonometry was initiated in my book, Divine Proportions, Rational Trigonometry to Universal Geometry, which was published in the year 2005 by my little company called Wild Egg. And you can go to the website and download the first chapter, which gives you some kind of overview of the approach. The book's also available at Amazon.com, and if you have a university library near you, ask them to order the book. Get it in there so that people can read it. It is a new way of thinking not just about trigonometry, but also Euclidean geometry. There's also a YouTube series that supports the book and that explains the theory from first principles. The series is called Wild Trig. You can find it also on this channel. And there are some articles in Wikipedia and elsewhere that describe some essential things about rational trigonometry. And if you'd like to, please feel free to add to those articles. And please feel free to tell your friends about this video and about this new way of thinking about geometry and mathematics. So today I'm going to present rational trigonometry to you. I'm going to assume you know nothing about it. This is going to be a first lecture. If you're a student, maybe a high school student, undergraduate student, graduate student, you're going to learn very important things. Make sure you understand everything that I'm saying in this video. If necessary, watch it several times. There are important exercises I'm going to give you in this video. So very important that you spend time and energy writing out the solutions to these exercises with care and diligence. If you're a professional mathematician, don't be dismayed by the elementary aspect of this video. You are going to learn something very, very important for you. You may not like it because it represents a reorientation of your mindset. To be honest, we've been indoctrinated as pure mathematicians into thinking in a certain, ultimately wrong direction. And you may not like it, but ultimately you will thank me for reorienting you to a much more natural and beautiful way of thinking about geometry, trigonometry, and mathematics more generally. So we're going to adopt a vector space approach today, which is very pleasant and very efficient way of encoding this theory. We're going to start today with the planar case, and in our next video we'll treat the three-dimensional case, one step up. So it's a very simple structure. We're working in the plane. We have points, we have vectors. A point is represented with square brackets, a vector with round brackets. The crucial definition on which everything depends is the definition of a quadrant. The quadrants of the vector v, the vector 2, 1, is 2 squared plus 1 squared. In general, it's the square of the x coordinate plus the square of the y coordinate. All our numbers are rational numbers. We are not pretending that we know anything other than those numbers. All of our quantities are going to be rational numbers. This is an important part of the power of this approach. The definition of quadrants is, of course, motivated by Pythagoras' theorem. Actually, Euclid's form of Pythagoras' theorem, the ancient Greek way of thinking about it in terms of one area of a square, another area of a square, added together makes a third area of a square. So, quadrants of a vector does not depend on a notion of distance. It is free of taking any square roots. There are no square roots in sight, and there will be no square roots in this theory. It's a purely rational theory. In this approach, I'm not going to assume very much sophistication. So our working with vectors is just at a very elementary level. If you would like to know a little bit more about vectors, I suggest the earlier videos in my linear algebra series, Wild LinAlg. So Pythagoras' theorem is the motivation for the definition of quadrants, but it's also the key to our understanding of perpendicularity. And that's because Pythagoras' theorem can be restated now this way with this idea of quadrants. The theorem is that two vectors v1 and v2 are perpendicular precisely when q of v1 plus q of v2 equals q of v2 minus v1. So why is that Pythagoras' theorem? Well, here's a vector v1 and here's a vector v2. Then the vector v2 minus v1 is the vector from here to here. So it's the hypotenuse side of this triangle. And Euclid's form of Pythagoras' theorem says that these two sides are perpendicular precisely when this area plus this area equals this area. Now this area is the quadrants of this vector, this area is the quadrants of this vector, and this area is the quadrants of this vector. So perpendicularity of these two vectors is exactly equivalent to the quadrants of v1 plus the quadrants of v2 equaling the quadrants of v2 minus v1. Now let's interpret that with coordinates. Well, suppose that v1 is the vector x1, y1, and that v2 is the vector x2, y2. Then the quadrants of v1 is x1 squared plus y1 squared. And the quadrants of v2 is x2 squared plus y2 squared. The vector v2 minus v1 is obtained by taking the differences between these vectors here. So it's x2 minus x1, comma, y2 minus y1. And so its quadrants is going to be x2 minus x1 squared plus y2 minus y1 squared. And then this condition up here becomes, in terms of quadrants of v1, quadrants of v2, and quadrants of v2 minus v1, this one plus this one equals this one. So there's the quadrants of v1, there's the quadrants of v2, and there's the quadrants of v2 minus v1. So let's have a look at this formula. What happens when we expand the right-hand side and cancel terms which are on both sides? The x1 squared, the x2 squared cancel with these ones. The y1 squared and the y2 squared cancel with these ones. The only thing that's left is the term minus 2x1 x2 plus minus 2y1 y2 equals 0. We can multiply by minus 1, and we can divide by 2, giving us x1 x2 plus y1 y2 equals 0. These things are equivalent. So we see that the perpendicularity of v1 and v2 is equivalent to this condition between the coordinates of v1 and the coordinates of v2. This is an application of Euclid's form of Pythagoras' theorem. But we are going to want our trigonometry to be independent of Euclidean geometry. We think that Euclid's Elements is a wonderful, incredibly important book. Far and away the most important mathematics text of all time. And it deserves much praise. But there are logical weaknesses in it. So we do not want to base our understanding of geometry on Euclid's work. It's what you have to do if you want to do things correctly. So with apologies to Euclid, it's going to be necessary for us to independently define all our terms, independent of any understanding of Euclid's geometry. We can be motivated by it, of course, and we are motivated by it, but ultimately the logic has to be independent of it. So let's start again with definitions. So we're starting right from the beginning, and now the story is independent of any pictures. It's purely algebraic. It's purely in terms of expressions created with rational numbers. First definition, what is a vector? A vector v equals xy is an ordered pair of rational numbers. It's not a directed line segment, it's not anything else, it's simply an ordered pair of rational numbers enclosed in round brackets. Our second definition. Here is how you add two vectors, here is how you subtract two vectors, and here is how you multiply a vector by a number. So all of the numbers here are rational numbers. These are the definitions of what we mean by addition of vectors, subtraction of vectors, and scalar multiplication of vectors. And now our definition of quadrants. The quadrants of the vector xy is, by definition, x squared plus y squared. It's the quadrants of the vector v, xy. That was motivated by Pythagoras' theorem and our understanding of Euclid, but it's now independent of it. It's just something that we're making up. We're saying that's what we're going to call the quadrants of that vector. And now here's the definition of perpendicularity. When are two vectors v1 and v2 perpendicular? They're perpendicular precisely when x1, x2 plus y1, y2 equals 0. Again, that's motivated by our previous discussion coming from Euclid. But the definition at this level is purely independent of it. It's just an algebraic condition on these two vectors. Either they're perpendicular or not, depending on whether this particular combination is 0 or not. And another definition, we'll say that two vectors v1 and v2 are parallel precisely when x1, y2 minus x2, y1 equals 0. If these were fractions, like x1 over y1, x2 over y2, this would just be the condition that the two fractions are equal. So another way of thinking about this is simply that this is the same thing as saying that one vector is a multiple of the other. This is a more symmetrical way of saying that. So there's no sense of extending the vectors and seeing whether the lines never intersect. It's a purely algebraic condition on the expressions we're using. It does not require any particular visualization. So we have a notion of vectors, we have a notion of vector arithmetic, very simple vector arithmetic. We have a notion of vectors being perpendicular and parallel, and we have the notion of quadrants of a vector. Okay, so now we can get to the two most important theorems in mathematics. So suppose v1 and v2 are vectors, and introduce v3 to be the difference between the two vectors, v2 minus v1. Define q1 to be the quadrants of v1, q2 to be the quadrants of v2, and q3 to be the quadrants of v3. Pythagoras' theorem says that v1 is perpendicular to v2 precisely when q1 plus q2 equals q3. The triple quad formula says that v1 is parallel to v2 precisely when this somewhat more complicated relationship is satisfied. q1 plus q2 plus q3 all squared equals 2 times q1 squared plus q2 squared plus q3 squared. We've really talked already about this, and the logical connection between here and here we've already essentially derived. This is something new. This is something that Euclid didn't really know. Although I suspect Archimedes would have looked at that and said, yeah, that sounds reasonable. This is a very, very important formula, even though it looks a little bit intimidating, but it's very nice and symmetrical between Q1, Q2, and Q3. Okay, I claim these are the two most important theorems in mathematics, and your first two exercises are to prove them. All right, prove these. The proof of this is already pretty well contained, so this one here, maybe you require some thinking. Remember, V1 parallel to V2 essentially means that one of them is a multiple of the other. Interesting and important theorems. Our next order of business is to introduce what's sometimes called the scalar, or inner, or dot product of two vectors. It's an expression we've already seen, and we're going to give it a name. We're going to say that the vector x1, y1 dotted with the vector x2, y2 is the number x1, x2 plus y1, y2. So it's some kind of multiplication or combination of two vectors to obtain a number. It's an absolutely fundamental idea in linear algebra. The importance of this inner product, scalar product, dot product, bilinear form, whatever you call it, it's hard to overestimate the importance. So here's a proposition that encodes a few simple properties of this product. First of all, it's symmetric. If you have two vectors v and u, then v dot u is the same as u dot v. Secondly, it's linear in the sense that if you take the sum v plus u and dot it with w, that's the same as taking v dot w plus u dot w. And because of this property, the same kind of linearity also applies if we interchange the order. So it's also linear in the second variable, but I won't say that explicitly because it follows from this one. There's also a linearity with respect to scalar multiplication. If lambda is a number, then lambda times v dotted with u is the same as lambda times the dot product of v and u. And that, by symmetry, is also the same as v dot lambda u. And finally, a vector dotted with itself gives you just the quadrants of the vector. So your third exercise, check these. Write down proofs so that you're absolutely sure that they're all true. All right, now we come to the second really important metrical notion that complements the notion of quadrants, which is the notion of spread. The spread between two vectors. Here's the definition. S of VU, so V and U are two vectors. This is going to be the spread between those two vectors, is defined to be this expression. It's 1 minus the quotient of V dot U all squared divided by the quadrants of V times the quadrants of U. And I remind you that the quadrants of V is really V dot V, and the quadrants of U is really U dot U. So there's really two dot products in the numerator, namely V dot U times V dot U. And there's really two dot products in the denominator, a V dot V and a U dot U. And this is called the spread between the vector U and the vector V. And we note that this is undefined if the quadrants of V is equal to 0 or the quadrants of U is equal to 0. We won't explicitly, in the definition, preclude those possibilities. We'll just agree that if we have a denominator which is 0, then the expression is sort of null and void and meaningless. All right. So this is a very important definition. It replaces the notion of an angle between two vectors. This is a much, much, much better notion of the separation between two vectors than is the notion of an angle. And I know if you're a classical pure mathematician, you'll balk at that and you'll say, no, no, that can't be. But I assure you it is true. And if you investigate it scientifically to see whether the claim is true, you will see that I am right. It is a much more natural, more beautiful, more elegant, more powerful, more computationally accurate way of thinking about the separation between two vectors. The notion of spread has some important properties that are described in this proposition. First of all, the spread is symmetric. The spread between v and u is the same as the spread between u and v. Secondly, that it's independent of scaling. So the spread between v and u is also the spread between lambda times v and u, which is also the same as the spread between v and lambda u. And if you combine those two things, you could further say that it's the spread between any multiple of v and any multiple of u, as long as the multiples are not zero. So it really only depends on the lines generated by those vectors and not by the vectors themselves. The spread really is a notion between two lines, even if the multiples are negative. So not rays, but lines. The third one is that the two vectors are perpendicular precisely when the spread between them is equal to 1. And the vectors are parallel precisely when the spread between them is 0. So your fourth exercise is to check these. The first three are all straightforward. The fourth one requires a little bit of a hint, perhaps. There is a lovely identity that goes back to Fibonacci. In fact, perhaps it goes back to Diophantus even earlier, which is this identity here. So you may find this identity useful to you to prove that number 4. All right, so now we have quadrants and spread. So let's think about a triangle, because trigonometry is about the study of a triangle. So suppose we have 3 points, A1, A2, A3, and then there are associated 3 vectors to those 3 points. And let's arrange that the vector v1 go from A2 to A3. So v1 is the vector A2, A3, and v2 is the vector A3, A1, and v3 is the vector A1, A2. These 3 vectors have 3 quadrances, and we're going to call those quadrances Q1, Q2, and Q3. So Q1 is the quadrants of V1. That's the quadrants of the side that's opposite A1. And similarly, the other way around. And then we have 3 spreads. So the spread S1 is the spread made between V2 and V3. The 2 vectors that are coming out or into A1. So this vector, these 2 lines make a spread. That's S1. S2 is the spread here, the spread between this line and this line. And S3, the spread between V1 and V2. And I denote a spread with a little straight line like this, and S3. That means it's the spread between this line and this line. And our notion for quadrants in a picture is a little rectangle along the side. Q3 means the quadrants of that vector there. So we have 3 quadrances and 3 spreads of a triangle. And trigonometry is all about the relationships between those 3 plus 3 equals 6 numbers. So here then are the 3 additional laws of trigonometry. And they relate to a general triangle with the quadrants as Q1, Q2, Q3, and spreads S1, S2, S3. The first is the cross law, which says that Q1 plus Q2 minus Q3 all squared equals 4 times Q1 times Q2 times 1 minus S3. So in particular, if you know Q1, Q2, and Q3, then you can solve for S3, the spread. And there's some symmetry here. This is really just one of three possible cross laws. This one sort of involves the spread S3, but there's also one involving S2 and another one involving S1. If we know two quadrances and a spread, then we have a quadratic equation for the third quadrant. This is a very important and powerful law. In fact, it turns out that this is the most powerful law, that all the other laws, in fact, if you look at it in the right way, are consequences of this particular single law. The spread law says that S1 over Q1 equals S2 over Q2 equals S3 over Q3. And the triple spread formula is a relationship between the three spreads of the triangle, and says that S1 plus S2 plus S3 all squared equals 2 times S1 squared plus S2 squared plus S3 squared plus 4 S1, S2, S3. That looks a lot like the triple quad formula, except there's now this additional cubic term with a 4 in front of it. So your next exercise is to prove these. And it turns out not to be very hard. So as a hint, you only really need to work with the dot products. You don't need to know anything other than what I've already stated in this lecture so far. You don't have to go back to the actual coordinates, just work with dot products. And at some point you may want to observe this rather useful identity, that the difference between the left and right hand sides of the triple quad formula can also be written or rewritten in this way, which sort of connects to what's happening in this equation here. So I suggest you prove the cross law first, and then prove the spread law as a consequence of the cross law, and then combine the cross law and the spread law to prove that one. And if you get stuck, well, you can go to my Wild Trig series, where you can see the various relationships between these things laid out. You can also have a look in my book. The point is that the manipulations necessary are not very hard. They are really at the high school level, although there's a bit of thinking to be done. So to summarize, starting with just some basic definitions of vectors in the plane, we have carefully and logically defined the main quantities of quadrances and spreads, quadrants of a vector and the spread between two vectors, and we have laid out the 5 main laws of rational trigonometry, which are Pythagoras' theorem, the triple quad formula, the cross law, the spread law, and the triple spread formula. And I've left the proofs of these to you essentially as exercises. And they are not hard, but I strongly suggest that you attempt them. Spend a few hours, or perhaps days, working it out and writing down the proofs. You will benefit enormously if you do this. Even if you are a professional pure mathematician, it will reorient you, or at least start to slowly reorient you. It's rather remarkable that this very elementary approach solves the vast majority of geometric, engineering, physics, trigonometric problems. And it does so faster, more accurately, and more logically than the classical trigonometry that you learn in schools. The classical trigonometry involving cosines and sines and tans and arc cosines and arc sines and pi and square roots. This is a computationally superior theory. So it's rather remarkable that this has been around since 2005, that's 7 years now. It's rather remarkable that my fellow mathematicians, my fellow pure mathematicians, have tried very hard to avoid acknowledging this revolution which is on their doorstep. They would rather not know about it. And I don't see a lot of effort in people actually taking to task this claim. It would be simple enough for people to say, let's get a working group together, let's investigate if Wildberger is actually right here. Because they probably realize that the consequences of seeing that I'm right are very dramatic. Not only is there a dramatic configuration of the geometrical landscape and the research orientation. But more importantly, there's this huge opportunity to dramatically simplify mathematics education. Because by making the switch from classical trigonometry to rational trigonometry, we dramatically simplify things. It's much easier to teach. It's much easier to learn. It's easier to use. Not just a little ways, it's enormously easier. You can see from this lecture what's involved. It's just elementary high school algebra. Calculators are not required. Of course, they're useful to make calculations involving big numbers, just because you have to multiply big numbers sometimes. But you do not need calculators to find transcendental function values. You can, in principle, compute things often completely accurately without any calculators. So it really offers students a whole new landscape of possibilities. And educators around the world really ought to be mobilizing to think about the consequences of this. Everybody acknowledges that there's a major problem with mathematics education. Here is a solution, at least for a large part of the problem, staring you in the face. We do not have to respond like deer in the headlights going, what does anybody else think about this? Let's have a look at the issues scientifically. If you're a listener, share this video with some of your friends. Pass on the information. Let's try to get things moving. Let's try to really be concerned about the education of our next generation coming up. They deserve a better approach to geometry and trigonometry, and this is it. So in my next video, we are going to jack this all up to 3 dimensions, because we want to talk about the geometry of the sphere, which is living in 3 dimensions. So if you've understood carefully what I've done here, it will be a snap extending this to 3 dimensions. So please make sure you understand everything that I've said today. Very, very important lecture. Very important that you do those exercises. Okay, these are the most important exercises in the course. So lots to do, lots to think about. Next time, rational trigonometry in 3 dimensions. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.